Hey everybody. I kind of left that last video somewhat abruptly, but I just wanted to show. So hopefully you worked on it, and if you didn't work on it, go back and work on it. How is the current related to the current density? So if I can go back here, this is where we left off. Whereas I thought, oh wait a sec, what have I done? Because I was thinking that J naught would just be a simple, an easy, simple function of the current, because normally it's the current density, right? So you normally would have something like uh, current divided by area. In this case, it's a loop, so it'd be pi r squared, uh, big R squared. And so let's go back up here. So if I look at this thing here, um, since the current density changes as a function of little r, what I was wondering about is, okay, well, what does it look like if I get to outside the wire? And outside the wire, we already know what the field should be, right? If we look back over here, this was the field inside the wire, and here is a field out there. Here it is. Here's the field outside the wire. I over 2 pi epsilon naught c squared r. So the field outside the wire should be the total I divided by 2 pi epsilon naught c squared little r. So when r equals capital R, we would like a continuous function here. So we need to make sure these two expressions match. Now, the reason that the B field should match the E field sometimes doesn't is because the B field has zero divergence. In other words, there are no spots where you can go over where there's an isolated magnetic pole. Now, when you went over something, when you went through a surface with charge on it, you had an E field before the charge, you had the charge, and then the E field after the charge. So there can be jumps in the E field because of the charge on the surface, but that's not the case in the B field. So when r equals r, then this field would just give you a capital R at the bottom here, like that. And then the question mark is, what's the inside field from approaching from the other direction? I would get J naught capital R squared. If I'm evaluating this at capital R, 3 epsilon naught c squared capital R. So that goes away and that goes away. And that does not look like what I want. Okay. So I'm going to undo those. And you can see the dependence looks all the R's in the wrong place. There's a 3. I got the epsilon naught c squared. That's good. And there's a current thingy on top, and there's a current thingy on top. So the question is, how do I make these two match? Well, it comes down to how is J naught related to I, which is what I was asking over here. What's the deal? How do I make this something where I can actually compare these two things? And that's when I said, normally you'd get something like this. But in our case, that's not what's happening. So I can either take the current density and find that as a function of the current, or I can do the current and find it as a function of the density. Point being that I do know what the entire current density, I'm sorry, I know what the current is inside the wire as a function of little r, and it's this expression right here, okay? So when I look at that and I say, what is it at capital R? That's like knowing the total current, all right? So that's 2 pi J naught, 2/3 pi J naught R over R cubed. Okay, so let me just write that down here. I is 2 pi over 3, and it was J naught over capital R times little r to the third. Now, if I want to evaluate this at capital R, in other words, I want the total current, right? I'm going to take this thing here, and I'm going to say, all right, J naught divided by R times big R to the third, and that goes away, and that goes away. So it looks like this. All right, that leaves you, since I'll do it this way, I'll substitute the current density for the current. Excuse me. So I'm going to flip this around and multiply it. Now this thing here on the left side has become the total current. Right? I've enclosed everything I can enclose. That's capital R. So now I'm going to get 3 divided by 2 pi, and I'm going to swing the r squared underneath, and I'm going to have an I divided by r squared. So you can see this is not a typical area expression. This is not I over pi r squared. This is weird. Okay, 3 over 2 pi r squared. So kind of strange-ish looking. Point being that it's 3/2 as big as I normally would have expected, right? Because if you look back here, I would have said, well, normally it's just this. Well, I got a factor of 3/2 in there now because I defined the current density. How did I define the current density? I defined it this way with R over capital R. So now I got a factor of 3/2 in here, which is kind of interesting. And what can I say? Obviously, I didn't foresee that. So back to the matter at hand, rather than perseverating on this, back to the matter at hand, I want to take this thing and put it up into there. So now that B is now 3 over 2 pi I over capital R squared multiplied by R squared. That thing right there in the parentheses is now J naught, right? Excuse me. So now what happens here is I'm going to get the R squareds are going to go away here and here. The 3 is going to go away there and there. And what I'm going to end up with here, now you see, look, my R is down here on the bottom. I've got a 2 pi, which is going to flop down here. I've got an I on the top. That's the only thing left that I'm seeing here. The 2 pi is coming underneath here. And lo and behold, it does work out. So, so that's nice. And that comes out of just a bit of fooling around with the current, right? And remembering that your current density and the current are related. And look, maybe it's not in the way you think. wasn't in the way I thought for me. And just keep an eye out for stuff like that so that you can rewrite the current density when you need to in terms of the total current, like in this situation. Okay, let's see. I guess there's one more thing worth mentioning. It's a bit of an aside. I don't normally mention this in class. Well, I mean, in like a normal class, because I know that you don't need to have had 5C, and you should have had 5B already, and you should be in 5C now. But that means that you may or may not have seen things like the divergence and the gradient and the curl. But just as a fun, here's something for funsies. Since since it doesn't really matter if I say this or not, because if you haven't had any experience with the divergence, then you need not watch any further, and I'll see you later. But if you have had some experience with the divergence, then I'm just going to show you a fun little trick here with the flux of current density of J dot dA. Okay. Now there's this thing in math called Gauss's theorem. Okay. It took me, I think somebody was telling me about this and I wasn't paying attention. So it wasn't until a bit later till I figured out there was a difference between Gauss's law in electrostatics, well, or electrodynamics really, Gauss's law, and Gauss's theorem, which is a math thing. So Gauss's theorem is that if you take let's see, I need to think of okay, just some regular old function. Function f. This has no physical significance at all, okay? Because it's a math theorem, so there's nothing other than math funsies in it, okay? So here's your function f, and you are thinking of taking f dot dA, like you're gonna find the flux of this function through a surface. I mean, they use the word flux. I don't know. Math people, I'm not sure they know what flux really is. It turns out that that's the same thing as doing the integral of the divergence of f. Okay, like that. Over a volume. So dv, I guess I'll use that way. But the thing is that you've gone from a surface integral, which you're looking at flux through, right? So I called that surface S, a surface area, and you've gone to the volume. You've gone to the volume of the divergence of this thing. So when I hear divergence, I think of the electric fields is the easiest thing because it's such a great example of a divergence. Think of a positive charge, the electric field. The electric field's radially outwards. If you kind of take that and you look at it from all different directions, you're going to see nothing but spikes coming all the way out, right? So if you enclose that with a Gaussian surface, then you're going to think about the flux going through the surface, right? All these spikes coming through the surface. And then you can also think of, well, how is the field diverging inside the volume, right? And what happens? So this is in this sense, this is known as the divergence of the function f. You see how it makes things much more concrete if you talk about something to apply these math theorems to, and they're great. And believe me, math is fun, I guess. No, it really is, but it's just like it's so hard for me to talk about math outside of thinking of how I was taught math, and how you're taught math is just, look, in my opinion, no good. All right. Anyways, point being that if I'm going to look at this in terms of the current density, all right, so I'm going to rewrite this in terms of the current density. I'm going to say, all right, well, look, I'm going to take j dot dA over here. It's through surface S, and I'm going to say that's going to equal the integral of the divergence of the charge. I almost said charge density. That would have been kind of a funny thing. dV over a volume here. The divergence of the current density, that's what it is. And the reason I was going to say charge is because the current density really is a flow of charge. Okay, so thinking about what the current density really is, you can think of the current density as like, so in the case of the electric field, there was nothing flowing, but in this case, there is. So this is something we can really get our hands on, because there is a, if I replace my positive charge and I have a current source there, and I'm just saying the current source is radiating radially outwards, it's pushing charge away, and I put my little surface over it, and I look at the net flux of charge flowing through the surface. I'm sorry. I'm not really sure what's going on here. So, and then I think of the divergence of the charge away from the center, the source, right? In that case, then I must have started with a charge right in the middle here, say plus Q, right? And it's radiating charge away like this in a kind of a J sense. Then the charge, this thing is getting less because it's pushing charge away. It's a finite charge and it's distributing current, and bits of it are flying off, right? Bits of this thing are flying off. That's not a big surprise. A positive charge is going to be repelled by positive charge. They're flying away. Okay, so little bits of positive charge are getting repelled. So this thing is decreasing. The amount of charge that I have in the center here is actually decreasing because there's a flow away from it. So if I think of the well, if I want to think of like the current flow, let's think of the total current flow away from the positive charge here, the total current flow, I. If I were to put it in terms of this positive Q right here, I would have to say it is a negative dq dt, right? Because dq dt is a negative number. It's the amount of plus Q in that middle is getting less. So d by dt of that positive charge is a negative number. So I need to say, well, my total current flow away from this thing is therefore minus dq dt. So what that means then is that if I think of this Q as being like a body of charge, right? There's a body of charge here with some charge density rho. Well, I would just do this because I would just integrate over rho dv to find the total Q, right? That's the total charge of the thing. So now look what happens. If I look back at this thing, oops, here, I look back at this thing and I say, okay, well, J dot dA, right? The current density flux through my surface is basically the total current flow, right? So it's got to equal, this thing here has to equal I, which is negative d by dt rho dv, like that. Okay. So that now by Gauss's theorem above here, where I have the surface integral being equal to the divergence, you can rewrite this in a divergence fashion. Come on, go up. There we go. Okay. So now this thing is also equal to a volume integral of the divergence of J d volume equal to negative d by dt rho dv. Okay. Essentially, but I have two volume integrals here, so just forget about the volume integrals. So what you end up with is that the divergence of the current density is minus, I'm going to have to use partials here because the charge density may be a function of multiple things. And this thing here is an expression of charge conservation, because what it says is the reduction of charge in the middle, the reduction of charge of something is equal to what it's throwing away from it. Okay, basically. So a little bit of funsies. That's also known as the continuity equation. But anyways, I'm going to stop there. Just a bit of funsies. Like I said, if you like the divergence and stuff like that, it gives you a little bit more physicality to think about the divergence. These aren't just mathematical quantities. These are real physical. These have real physical meaning. It's just that you never see it because the math people don't know the physics of it. So, all right. Anyways, so hope you enjoyed that, and I'll see you next time.